So, good morning, everyone. It's a great pleasure for me to introduce you Vidya Madhava. She's professor of condensed matter physics at the University of Illinois in Urbana-Champaign. She made a PhD at Boston University in physics, and then she moved to Berkeley, University of Berkeley. For people doing STM, she published, I don't know if it's the first or the second paper, on the first, sorry, because there were two papers in the same year, one in science and the other in physical regulators about the conduct.
Yeah, I
Resonance.
actually don't know whose paper was
That, I don't know, there were two papers, one in science, another in physical
but
regulators.
we claim that ours is first because ours is, we know it's individual
Okay, so she published the first paper. Quantum resonance measured with.
Wait, is this being recorded?
Yeah.
No, I'm not sure.
Well, one of the two first papers that measuring the quantum resonance with STM, and then she made a number of contributions in different topics in condensed matter physics, like I have here the list because otherwise I will forget some of them: topological systems, two-dimensional materials, Majorana quasi particles, highly correlated electron systems, and also, of course, STM, synchronized STM, and growing two-dimensional materials using molecular kinetic activity. Among recognitions, in 2015, she was elected Fellow of the American Physical Society. 2021, the Fellow of the Canadian Institute for Advanced Research. 2020, Gordon and Betty Moore Foundation Fellow, and in 2023, she was appointed as member of the American Academy of Art and Science. So, because you can't hear Vidya and myself, so the floor is yours, Vidya.
Thank you. Thank you very much. I have to say thanks so much for inviting me. It's a real pleasure. It's the first time that I'm visiting here to the university. I've come to Madrid before. And so before I start, I assumed this was going to be a colloquium, so I had some introductory slides. But now I'm thinking, all of you are STM people? Good. So, but given how much STM goes on in this institute, I'm going to basically go very quickly through the first part. So everyone can hear me, right? I'm pretty loud. Yes, I'm not going to use the microphone. Before I start, so this work, it's a new exploration for us. We decided to build this new instrument to couple light with STM, and essentially our goal was to study get time resolution. And so that's what I'm going to talk about today. How can you get time resolution? What kind of information can you get? And so it's been a pretty long endeavor. It's taken us 5 years to get to this point. But I think now I can say pretty confidently that we can get femtosecond time resolution. So our time resolution right now is 70 femtoseconds. And I think we can get even to half of that pretty easily. And it's quite exciting to be able to do this. So the people who built this instrument and really solved, I can't even tell you how many technical problems for us to get to the stage, are Asokjan Bey, my postdoc, and Arjun Raghavan, my student. And for given the work that I'm going to talk about today, we had theory help from Barry Bradlin and Ziqian Guan. And we got single crystals from Daniel Shoemaker's group, who's also at UIUC. So you're all familiar with the origins of STM. Binning and Rohr built the first instrument in 1981, and it was immediately recognized how powerful this instrument is because they got their Nobel Prize in 1986. As you know, the STM, it's extremely powerful. We have picometer spatial resolution. We can measure density of states with microvolt resolution, depending on the temperature, of course. And there is this really nice quote by Niels Bohr, which says that a physicist is just an atom's way of looking at itself. And so that's what a physicist is. And I would say, from the perspective of an STM, an electron is also an atom's way of looking at itself. Okay, and since you're very familiar with STM, I can go quickly over this. Essentially, this is just to show you how powerful STM is. You can get beautiful images. This is an image of the superconductor FESC. And now if you add some tellurium to it, it looks like this. The inhomogeneity that you see is electronic. And in fact, this is the superconducting gap. And you can see how the coherence peaks change as a function of position. And all this inhomogeneity in the superconducting properties come from the inhomogeneity in the electronic properties. With STM, you can not only measure density of states and see beautiful images, but you can also get spin resolution. And this is an example of the other end member of the series, iron, selenium, tellurium. One end is a superconductor. When you add tellurium to FeSc, you also get a superconductor. By the time you get to the other end, it's an antiferromagnet. So this is imaging the tellurium atoms on FeTe with a normal tip. But then if you have a magnetic tip, you can see these stripes. And these stripes are basically the antiferromagnetism at the atomic scale. You can also do DIDV maps and look at quasi-particle interference. This is a DIDV map on bismuth telluride, which is a topological insulator. And you can get band structure information from such maps. Okay, so STM is, from the time it was invented to today, we've seen a huge growth in the capacity of what STM can do. You never imagined when you first started doing STM that you would be able to get momentum space information. One didn't imagine that you would be able to see spins. And certainly one didn't imagine that you could see Cooper pairs directly, which you can if you have a superconducting tip. So the STM has come a long way. The nice thing about STM, of course, is that we have gating, we have temperature control, we have magnetic fields. So using all these techniques, we can see all kinds of things. Electron phonon coupling, for example, we can visualize all these different order parameters, look at phase transitions. So the question is, what is the next frontier? And I would argue that the next frontier really is time resolution. So let's talk about time scales and solids. So let's just take a very simple example. Supposing you have an insulator, and this is the ground state. You shine a pulse of laser light, the first thing that happens is electrons get excited from the valence band into the conduction band. And then the question is, what happens and over what time scales? The first thing that happens is that you have electron-electron scattering, and that happens really quickly, like within a femtosecond, a few femtoseconds. And that causes some of these electrons from the higher energy levels to go back to the valence band. But then over longer time scales of picoseconds, right? Remember what a femtosecond is, it's 10 to the minus 15 seconds, right? Over slightly longer time scales of picoseconds, you have electron phonon scattering. And now is when the system starts to get thermalized, okay? Because until you have just the electron-electron scattering processes, the electrons are really, really hot. You can imagine they're thousands of kelvins, but the solid is not hot because the atoms are not yet vibrating. But then once the electrons scatter with the atoms, right, then the atoms start getting heated up, and then you have the atoms themselves getting slightly hot. Now, the atoms are really much fatter than the electrons, so the actual temperature of the sample really doesn't go up very much, okay? But initially, the electrons are really hot. Anyway, so this thermalization occurs over femtoseconds to picosecond time scales. The question is, how do you get femtosecond resolution from STM? And we all know that the STM is, sometimes very frustratingly extremely slow. It takes us minutes to take an image. It takes us days to get the IDV map. At the best, you can get maybe microsecond time resolution if you try really hard. But to get picosecond or femtosecond time resolution is extremely difficult with the scanning time microscope. They have these cables, they have capacitance. It takes time even for a signal to go from the STM to the top of the fridge. There are many constraints. So the answer is light. And this idea that you can use light to get time resolution is actually really old. In fact, this is just a brief history. very quickly, within 10 years after the invention of the first SPM, people started thinking about how to use light to get time resolution. And so they realized that you can combine pulse laser light. And in fact, the first results were reported in 1991, where they got 10 nanosecond time resolution. Now, nanoseconds is not fast enough, right? Nano seems really fast, but 10 nanoseconds is simply not fast enough to capture dynamics. However, this was a really great first step. And then over the last few decades, we've actually made a series of inventions. And I have to tell you, some of these inventions have come from the optics side of things. And so that has also helped us to get where we are today. And so there's also this technique in 2002 of this shaken pair pulse excited STM. You don't need to know what that is all about. But basically, what this allowed us to do was to get to picosecond time resolution. But finally, I think it's only the 2010 and after that the signal to noise of the scanning tunneling microscope, this dynamic probe, has gotten good enough to see real excitations. And essentially, ultrafast STM has been, there's been a lot of work on molecules, or like you have proof of concept in gold, silver, gallium arsenide, diselenite. But then our goal has always been to basically use this kind of an instrument to study quantum materials, right? And so what are we really interested in terms of physics? Really, what inspired us was this idea of light-induced superconductivity. So there's been all these reports that you can take a superconductor, and if you shine some pulse laser light on it, for a short time after you illuminate the system, you can get superconductivity, which goes to 2 times or 3 times the transition temperature. And in fact, there are some suggestions that you can even take a material that's not superconducting, maybe very close to superconductivity, and bring light induce superconductivity at pretty high temperatures. So this is one of our inspirations. Another inspiration is light is really cool because light does many, many things. And one of the things it does is break time reversal symmetry. If you have circularly polarized light, then you can break time reversal symmetry. And using that, you can actually, for example, create a gap at the Dirac point. You can have chiral edge modes because you're breaking time reversal symmetry. So light is another control norm, really. So this is the instrument that we've built. It's a really simple system in terms of concept, but of course it's taken a while. This is a commercial SCM from Unisoku. It has this optical access, and here you can see our table with all the optics. So we have a high-powered pulse laser, and then we have all this optics, and I don't need to go into this. There are a few important things I should mention that are important to get this time resolution. The first is we need to be able to focus the light to the tip sample junction. So that means that you need in our UHV chamber, you need these lenses to focus. So our lenses are really, really close to the SDM tip. So they're like very small distance away from the SDM tip. So we can focus the light to 10 microns. And so here you can see the tip, you can see the light, and you can see the reflection of the tip. The important thing here is, imagine you have a tip and you have this laser spot, and the laser spot is only 10 microns, and you can miss it, right? You can miss the area where the laser spot is illuminating your sample. So you need to be able to position the tip on top of the light. This used to be a big problem, but because we can see, it makes life a lot easier. We can actually position the tip right on top of the spot. Okay, so how does this work? So here's how it works. You have this here is your light, the light pulse. And what I'm showing you in red is the response of the sample. Okay, so this is so as soon as this light pulse hits the sample, there is some process that happens. There's some excitation. Many things are excited in the sample, and that this is your initial excitation. And then over some period of time, the sample relaxes back into equilibrium. So that's what this is capturing. So we have two consecutive pulses. So then this is the second laser pulse, and then the same thing happens. And what we do is vary the time difference between these two pulses. So when the two pulses are very far away from each other in time, then the system has independent response. But when the two pulses start overlapping, then the response of the system is not the same because the system hasn't fully relaxed. Okay. So what we do is we measure average tunnel current. This is the tunnel current that we're measuring is just an average tunnel current. And we measure this average tunnel current as a function of the distance between these two pulses. And that's basically how we do our experiment. Okay. So if you think about what you expect to see is that, let's say there's some, this is the response. When these two pulses are far away, everything just adds together, right? And so you get some response in your system. And then as the pulses get closer, then you can imagine for one situation might be that if this is almost overlapping, the response to the second pulse might be extremely weak. So the tunnel current that you get might be much smaller than in this case. So that's really in theory what is supposed to happen. When my postdoc first proposed this to me, I really did not think it was going to work. But, I hope today to show you that this technique actually works. Okay, so the system that I'm going to be talking about today is this Wiles charge density wave system, tantalum, selenium, iron. So before I jump into this, let me just give you some motivation for why this might be interesting. So in order to do that, I want to talk about the Higgs mechanism. So as you know that, there was a Big Bang, and as the universe cooled, the Higgs field acquired a non-zero expectation value. So basically, it acquired this Higgs field acquired some amplitude and also a phase. And because of this, symmetries were broken. For example, electroweak symmetry was broken into electromagnetic and weak forces. And then due to interactions with the Higgs field, the weak force carriers became massive, and they became short-ranged. And in this process, the Higgs boson also became massive. So the interaction between the Higgs boson and the other bosons made both of them short-ranged. Okay. And basically, the same mechanism is responsible for the finite penetration depth of magnetic fields in a superconductor. Because in a superconductor, you have a condensate. So remember, this is what you do. You have something to condense. For example, the Higgs condensed. In a superconductor, you have the condensate of the Cooper pairs. So you need a condensate. The Cooper pairs, that field acquires a non-zero expectation value. And then when you have a photon, which is what a magnetic field is, going into your superconductor, the interaction between the photon and this condensate makes both of these things short range, which means really that the magnetic field cannot penetrate into your superconductor. So that's the mechanism. So the question is, what does this have to do with the charge density wave system? And I think I've also already given you the answer. Basically, now let's consider this charge density wave. A charge density wave is a static charge order that breaks the crystalline symmetry of the lattice. And that means the charge density wave, just like the Higgs field below the CDW transition, has an amplitude and a phase, right? And it also breaks the symmetry of the crystal. So these acquire non-zero expectation values. The excitations of a charge density wave there are two kinds of excitations of a CDW. One is called a phason, and the other is called an amplitudon. And it's these excitations that I'm going to talk about today. And what I'm going to show you is that the interaction of these excitations with Coulomb interactions, and you remember the carriers of Coulomb forces are also photons, these interactions can generate something like the Higgs mechanism and make one of these excitations massive, just like the Higgs mechanism. And yeah, so that's what I'm going to tell you about. So let me just start with the excitations of a CDW. So remember, a charge density wave is like a, just a density wave in your solid. So what kinds of excitations can it have? One excitation is called the amplitude-on, and you'll see in a second why it's called that. It's just the amplitude of the CDW oscillating in time. So it's called with some frequency. That's the amplitude-on. The other excitation is the phase-on. This is the phase of the charge density wave oscillating in time. So if you look at this is the amplitude oscillating in time, and this is the phase, this phase oscillating as a function of time. Now that's in the time domain. In the frequency domain, what does this look like? So what it looks like is when you enter into this charge density wave phase, this is the frequency and this is momentum. Okay. So this what I've drawn here is one of the phonons of the system. This is the longitudinal acoustic phonon. Above the CDW transition, you just have some acoustic phonon in the system. This phonon is a lattice vibration, right? Now, if you go below the charge density wave transition, at the Q of the charge density wave, this thing softens, and the amplitude and the phase mode look like this. So this is the dispersion of the phase mode. The fact that it looks like this and goes to zero right, the frequency can go to zero, tells you that the phase mode is massless. It usually has no mass. And the way to understand it is think about a 1D charge density wave, which is incommensurate. The fact that it's incommensurate is really important. That means it's not locked to the lattice in any way. The phase mode is just the shifting of the entire CDW in space, like this. There's nothing locking it to the lattice. It's very easy to move it, and so it has no mass. It has no resistance to motion. Okay? The amplitude mode, on the other hand, is always massive. All right. Okay. So that's what occurs in a normal charge density wave. Now, what if you had a very special charge? So 99% of the charge density wave systems we know are metals. And the reason a CDW is a metal is first, if you want to go down to below the charge density wave transition, and if you want this to be a stable phase, you want to have some energetic difference between your parent compound and the CDW phase. And for that, you need to have electrons of the Fermi energy, because those are the ones that give you the CDW, and then you get a gap, and that's what gives you the extra energy. However, however, this gapping that I'm talking about is not a full gap. The charge density wave usually connects only some pieces of the Fermi surface, and usually you only get a gap along those connections, and the rest of the Fermi surface remains intact. So if you start with a metal and go into the CDW phase, you'll get a tiny little gap, but the system remains metallic. What if you had a system where in the charge density wave phase, you actually had an insulator? This is not usual, but it does happen periodically. And if you have such a system, something really interesting happens. Normally, when you have a metal, because of all the electrons, Coulomb interactions are really well screened, right? So that's what a metal is. But if you have an insulator, then Coulomb interactions are no longer well screened. And that means that when a charge density wave starts oscillating, it experiences Coulomb forces due to the fact that Coulomb interactions are not well screened. And in fact, what happens is because of the interaction with these Coulomb forces, and here's the Higgs mechanism, the charge density wave excitations interact with the Coulomb forces, and this massless phase-on, this one, really becomes massive. So it's no longer seen at zero frequency. It has a finite frequency. The lowest energy that you need to excite this mode is actually finite. So you need some energy to excite the phase mode. That's what happens when you have these strong Coulomb interactions. So this was predicted in the 1970s. There were a series of papers really in the 1970s about this mechanism to provide mass to the phasons. But the problem has always been that it's really hard to find insulating charge density waves. So now that brings me to this compound, tantalum selenium iodide. Tantalum selenium iodide, it turns out, is really a very, very, very strong insulator. In fact, for STM people, we can't go much below 70 Kelvin, right? That's all. If we get below 70 Kelvin, we can't tunnel, we can't do anything with this. This is what the STM image of the CDW looks like. You can see these stripes. This is the charge density wave. And in the Fourier transform, you can see it's these two dots. It's incommensurate. This is a pretty large wavelength, CDW. And it's not even in the primary directions of the atoms. It's in some strange 43 to 45 degrees. It's huge. It's, 9 nanometers, the period of the CDWs. So you can see from STM spectra that it's got a pretty large gap. It's 2 delta is 220 MeV, and it's a very robust insulator. So the thing that I want to now look for is signatures of this massive phase mode of this charge density wave. And there are actually two signatures that one can imagine. So the phase mode is this oscillation of the phase of the CDW. This creates, if you have a phase changing as a function of time, it always gives you a current. It's a superconductor, it doesn't matter what the phase is, but if you have condensate and the phase changes as a function of time, you get a current. In this case, the phase is changing as a function of time, that gives you current, and you can measure that with something like STM or point cloud. The other thing it does is because charge is sloshing back and forth, it must radiate. So it gives you radiation at the frequency of this oscillation. So the first measurements on the system, oops, I don't know what I did. Okay. The first measurements of the system were done using terahertz spectroscopy by my colleague Manu. The way they do the experiment is very much like ours. They have a light going in, but then instead of looking at the tunnel current, they look at the radiation coming off of the sample, terahertz radiation. And what they find, this is their terahertz electric field, and they take a Fourier transform of this, and they find a peak at 0.22 terahertz, okay? And how do they know that this is a massive phase? The way they at least this is the experimental observation, you measure the intensity, the height of this peak, as a function of temperature. The charge density wave occurs, the transition happens at high temperatures, like 220 Kelvin or something like that. I can't remember, some 200 something Kelvin. Does it say here? No. 260 Kelvin. And then, but at some other funny temperature of 0.3 times CDW, which is around 80 Kelvin, you can see the intensity above that temperature is really low, actually 0. But as soon as you hit this temperature, the intensity sharply rises and then saturates. So the sharp rise in intensity is basically a signature that this thing is a massive phase mode. The reason you have the sharp rise in temperature at a temperature very far from the CDW transition is because at this temperature, the velocity of these, the phase velocity becomes much faster than the electron velocity, and screening is not good enough. And so basically the mass comes from poor screening, and there are two contributing to screening. One is the number of quasi-particle excitations you have, which is already very small because this is a very good insulator. And the other is how fast can they move to screen. And basically there's a conspiracy between these such that at 0.3 TC, the screening becomes very, very bad. And suddenly you see this massive phase mode emerging. So that is their experimental observation. And that's their proposal for what this is. Okay, so the question is, of course, if this is true, then we should be able to see it in STM. We should be able to see current oscillations They're just seeing the radiation, right? We should be able to see current oscillations associated with this phase mode. Okay. So this is our now our measurement. The data I'm going to show you, I have both tunneling data and we also push the tip into the sample. To do temperature-dependent measurements, we use point contact because otherwise the tip keeps changing at different temperatures, and we really want to compare the intensity of this peak at different temperatures. But let me just show you the data. So this, just to remind you, this is how we do the experiment. And now, before I show you the data, let me just tell you a couple of things. One is, this is not that important. Yeah. So the way it works is we have these pairs of pulses, right? And then we have something called a pulse picker that either picks even or odd pulses, okay? And then let's say it picks only the even pulses, right? One of these channels. That goes through a delay stage, right? And then that gets to the sample. And then we have another channel that picks what the other pulse, and that also gets added and goes to the sample. So that's how we control the delay between these two pulses. That's all I wanted to tell you. Okay. And in our system, this is something really important. We are using a log-in to measure the difference between two pulses, the current with two pulses being close, and the current with two pulses being pretty far apart. And the reason we do this is by doing this, we get rid of the tip thermal expansion. Because remember, every time you hit the system with light, the tip is also getting hit with light. That means the tip is going to expand. So how do you separate actual data from tip data? And the way we do it is by taking a difference between these two signals. Because for the purposes of the tip, whether the two pulses are separated by, 100 femtoseconds or 1 picosecond makes no difference. So it's still going to expand thermally. So we just subtract the two signals from each other. Okay. This is just for anyone who's interested. I mean, this is what we're very proud of, the time resolution. We have huge fluence. We can melt the sample, basically a huge amount of power. This is our pulse width. And these are the parameters we used for this experiment. Okay, so let me just show you what we see. This is average tunnel current as a function of time delay. We see oscillations, which is quite amazing. Look at this time, it's in picoseconds. So these are really femtoseconds separated. And then in tunneling, we see the same thing. We see oscillations. You can take a Fourier transform of both the point contact and the tunneling. And in both of these, you see two peaks, one at 0.11 terahertz and one at 0.22 terahertz. Okay. And so from now onwards, for the current measurements, I'm just going to focus on the point contact, essentially because you can see the signal to noise is much better here. And also for temperature dependence, this is much better. But I wanted to show you this just to show you that, we can really do spatial dependence of the tunnel current and get spatially resolved dynamics, which is pretty neat, which you can't do with point contact. Okay, so now let's do temperature dependence, right? First, you should already be intrigued. Parts are one mode at 0.23. We're seeing two modes, one at 0.22, one at 0.22. And you can already see from here that these two are almost the same amplitude. So it's not as though one is the harmonic of the other. Okay. So in this system, there's only one longitudinal acoustic mode, and there should be only one phase zone associated with that that's massive. So these two cannot both be massive phasons, right? You might say, hey, maybe this is the primary, this is the secondary, but you can see the amplitude of this mode is almost the same as this one. It doesn't look like one is the secondary of the other. So there's something already different about our data. Okay, so now let's look at temperature dependence and see if we can reproduce Fahard's temperature dependence. So this in green is Fahard's data, and in blue is the 0.22 terahertz mode. This was also 0.22, and they literally fall exactly on top of each other. So this is quite exciting. This means that the radiation that we saw, the terahertz signal, is really due to current oscillations, which is what we're measuring with our ST. But then let's ask, what about the 0.11 mode? And sadly, that also has the same temperature dependence, which as usual makes life very complicated. Now you have to explain why two modes have the same temperature. Okay, so we have only one massive phase-on. Yeah, so this is all to show you that there's been, neutron scattering measurements which show only one longitudinal acoustic mode, which means that there's only one massive phase-on. Okay, so what about the amplitude mode? Now, there's no reason to expect that the amplitude mode should be half the phase mode, but maybe it is. And in fact, X-ray studies, this is time-resolved X-ray. Someone here wants to do time-resolved X-ray. And so this is time-resolved X-ray that show that you see this, if you sit on top of a charge density wave peak in X-ray, right, you can sit on top of it and watch how it oscillates as a function of time. It's the same experiment we're doing. You pump it with some pulse light, and you watch the oscillations of the CDW peak. You see that it oscillates at a frequency of 0.11 terahertz. So this group suggests that there's an amplitude mode at 0.11 terahertz. But the problem is that this strange temperature dependence that I was talking about, that's only expected for a massive phase-on and not for the amplitude-on. And in any case, there are reasons to think that we don't actually see the amplitude mode with the SPM. So there are mysteries. And so after thinking about it for a while, we came up with one possible idea. And here's the possibility. There's something called parametric amplification. It's a complicated sounding name, but actually in reality, it's a really simple thing. The idea is that you have this particle, which is your phase-on, and it splits into two. Okay, and so what does it split into? If you have another mode right below it, another phase-on, this is not massive, this is massless. Basically, this mode can split into two particles with equal and opposite momenta and and the same identical energy. So half the energy of this one. So this process is allowed. So this process is called parametric amplification. And so what we think is going on is that you have the 0.22 terahertz massive phase-on, and it's splitting into these two massless phase-ons by this process of parametric amplification. And it's really simple, similar to the decay of a particle into two particles. So, then we're left with two questions. One, we have two modes. When we dynamically excite the system, we have two modes at 0.11 terahertz, right? We have a problem now. We have the massless phase-on that I just said, I'm speculating, and we have the amplitude. It's also at 0.11 terahertz from the X-ray studies. So the question is, do these guys interact with one another? This is like a dynamically excited system. You have these dynamic excitations. Do these things interact with one another? And to answer that question, we actually in the same SCM, we have another technique, which is pump probe reflectivity. And the way we do it they're called the pump and the probe here because they actually are the pump and the probe. The pump excites the sample, and then we measure the reflectivity of the probe. So we're able to basically take away the pump because they're differently polarized. So we have a polarizer that kills the pump and only sees the probe. And we measure the reflectivity of the probe. So we're doing a time-resolved reflectivity measurement. And this is our time-resolved reflectivity data. Again, you see lots of oscillations. Interestingly, you also see the slower oscillation, and that's the 17 gigahertz mode, which I'm not going to talk about today. But in this time-resolved reflectivity, you see two other modes, one at 0.11 terahertz, and the other, a much smaller one at 0.22. This intensity difference is telling you that this is probably just a second half. Okay. Now we can look at the temperature dependence of this, and it's completely different. So this is the terahertz mode, which is what our 0.11 and 0.22 STM modes look like. This is the mode that reflectivity measures. And the question is, what is this and why does this intensity go down right when the intensity of this is going up? And the answer is now, when you put everything together, it all makes sense. Essentially what happens is, sorry, it's here. So as this phase-on mode intensity increases, not this one, but the 0.11 mode intensity increases, the amplitude on basically gets suppressed. That is the answer. So this is the data that we have. We have the point contact and STM showing the existence of two modes, one at 0.22, which we believe is the massive phase-on, the other at 0.11, which is a parametrically amplified massless phase-on. That massless phase-on competes with the amplitude on, which we see in our reflectivity measurements. So that's the story. Okay, so this is the summary. Oh, that's pretty fast. Okay, this is the summary. I can go on and have another talk right after this. No, I really do actually, but we don't have. I'm kidding. You can ask me questions. So this is the summary. So we have this new technique. We can do reflectivity, time resolved point contact, time resolved STM, tip enhanced photoluminescence, all kinds of measurements with one instrument. We can see these charge oscillations, the massive phase-on, the mass acquisition mechanism is analogous to the Higgs. I don't know why I have a comma. And then there's a dynamic competition between the phase-on and the amplitude on in this system. Yeah, thank you for your time. If you're interested.
For the social media, we keep my question. So the questions? Okay.
Thank you so much. Really beautiful talk. Is there any chance to use this technique in the context of superconductivity? Because after all, I mean, we're motivating this with the Higgs.
Yeah, so we have some constraints. We have 4 Kelvin, and maybe we can pump to get 3 Kelvin. But so we would have to find a superconductor that superconducts, but there are many, right?
Yes.
This technique is still new to us, and we don't really know under what conditions we can get a signal and what conditions we don't get a signal. For example, I don't think you can see the amplitude mode with this, at least with the point contact, they showed it cannot. But with the Higgs, we want to see the amplitude mode, right? Yeah. But we might be able to, maybe we can park ourselves at the coherence peak of the superconductor and see that oscillate as a function of time. That would be pretty amazing. So I think there are things we can try, which we haven't done yet. We're slowly understanding the instrument better and better as time goes on. But we're definitely going to look at all kinds of superconductors, including Q rates and so on. So yeah, we'll see what we can see. Yeah. One nice thing about this, the way we have this set up is we have the capability of doing spectroscopy. So unlike terahertz STM, we can actually change bias and measure the response of the system at different bias voltages. So like I said, we can park ourselves at different biases, including the particular coherence peak, and see what happens as a function of time at a particular bias, which is pretty cool.
Yeah, good luck.
Thanks.
You're welcome.
Yeah, beautiful talk. I have, first, I guess that is implicit in what you said, but I'm not familiar with the technique, so I was wondering. So, in your reflectivity measurements,
yes.
the last ones you have shown, basically you see a peak at 0.11 and 0.22, and then is it then obvious that when you say reflectivity measurements, it's only the amplitude and not the phase-on?
Yeah, because of the temperature difference. So it's basically a lot of this analysis and the idea of the massive phase-on it rests on this strange temperature dependence, which is this increase in amplitude, sudden increase in amplitude at this very strange temperature, which has nothing to do with the CDW transition. So this increase in amplitude basically is really zero here. Also, the X-ray studies were measured about at around 150. The phase mode is zero at 150. You see nothing. Even in STM, we see nothing. So X-ray studies that see the amplitude mode, they see this thing, right? This temperature dependence is exactly the opposite of what you would expect for the phasor.
Right.
So it all rests on this temperature.
And then the peak at 0.22 there should be understood as the second harmonic of the amplitude.
Yeah, it's very tiny, and in fact, it's almost zero for most of it. Let me show you the data. So it's very difficult to see this peak, and so it's behaving like you would expect a second half.
And the second, I also think it was implicit, but just to make sure. Then I understand that your current understanding is that the matching in frequency of the massive phasons and the amplitude is serendipity.
Yeah, I kind of understand where they're starting from. In fact, it's very peculiar. But but the only thing I take comfort in is that if I take all the data that we have, the terahertz data, the fact that there's a radiating mode, the fact that we see current oscillations, the fact that everybody has the same temperature dependence, the fact that X-ray is actually literally watching the CDW oscillate up and down. If I take all of that, there's no other explanation apart from the one I just proposed. So I'm open to other explanations, but so far we found none, and it is indeed a real mystery why one is the half of the other.
Thanks for the beautiful talk. I would like to understand better what do you mean by the solid contact.
Oh.
What do you mean actually that from making the measurement? It can operate your attempting the sample in other way.
Am I doing what?
Making the point contact.
Yeah, I can go to that. It's nice because it's STM. Life is easy. What I mean by easy is just in case my postdoc is listening.
Pushing hard.
Yeah, exactly. So we just slowly bring the tip closer, and we know when we are touching. And then beyond that, we push a little harder. And we have done distance dependent measurements. And so, yeah, if you go too deep, then you start losing the signal. It's probably creating pressure. So our signal strength depends initially on how hard they're pushing, and then we start losing our signal. I can tell you that we're extending the read, but how deep it's going is a completely different story. When we withdraw an image again, we can, depending upon how much we push, we can see the little damaged area. It's not very big, it's nanometers. So it's a pretty nice little point contact. And it's really not damaging large areas.
Okay, but you said that the reason for that was that if not, the thing was changing with that.
So the thing is that if we do STM, so because we're so interested in the actual relative amplitude at different temperatures, when you shine light on the tip, because we do so many temperature measurements, the tip changes. Like once in a while it'll drop something, and then when it does that, the STM signal, which depends so sensitively on the condition of the tip, its intensity will change. So how do we know, right? So we, instead of bringing our heads against having this tip change and trying to figure out what to do about that, we just did point contact for this experiment because life was easier.
That's not the sensitivity, but that's not actually an advantage.
For this, but the thing is, it would be really cool to do the STM experiment, and we may have to do it many times to get the data. But it would be really cool because we have two peaks in STM at 0.11 and 0.22. But I actually have no idea whether those two peaks are these peaks. Right? In point contact, for sure, we're seeing the temperature dependence behave identically. The question is, what about the STM peaks, which would be really interesting as far as I'm concerned, but we haven't done it yet.
Okay, thank you.
Okay. Alan?
Yes, thank you, beautiful talk, incredible results. But I had a question about your time traces. So there's something a little strange to me about them. Which is it looks like your two modes actually decay with very different time constants.
Yeah.
So here, so here your 11 terahertz mode decays 2 or 3 times faster than your 0.22 terahertz mode. But under the mechanism you described, I would have expected this mode to actually rise at later times.
It does. I think this is really complicated actually. So this is beating.
Yeah.
They're beating, right?
Yeah, so then
And also,
you can see by 60 picoseconds, you've gone to almost a pure mode.
yeah, but there is also another problem that actually. So these things, they have shoulders, which you can't see here, but you can see it in some other. So there's also something else. There's also some low frequency thing that's creating. I don't know what it is. Either it's another frequency or we haven't figured out what this shoulder is exactly. So that shoulder, so there are many problems with doing a time. We've tried this. We've tried to see which one arises first, which one arises second. There's also a decaying, we've subtracted it, but there's a decaying time constant initially. I have time dependent, we do an inverse Fourier transform. And I have some analysis of that. It all looks different whether you include these shoulders or not. So, yeah. So we haven't quite understood all the details of yet.
And the same for the reflectivity data, because there it looks like the two components stay pretty much together the entire time. Again, if it was a second harmonic, I would expect it to die off roughly twice as fast as a fundamental. But here, for instance, it still looks like nice square alpha waves out to about 50 picoseconds.
You mean these guys, right?
That's the signature that you have the second harmonic.
Yeah, and again, I think one has to actually remove. We can check. One has to, but I mean, so the one interesting thing is this reflects this. So there are two things to this. One is the height of the peak and also the full width half max. And I guess the full width half max here, if it's similar to here, probably tells you that they're sort of living similar times. Yeah, I'm not sure why this should die out faster than this if it's a second harmonic.
Well, because it goes as the square of the amplitude, right? So
okay,
you double the exponential.
Yeah, but do remember that this cannot be the terahertz mode, the radiating mode, because of the temperature dependence. Yeah, so
I think you can also use symmetry rules to argue that if you like, because it radiates the terahertz radiation, you cannot modulate the reflectivity in this one.
Okay, thank you. So yeah, so if it's not the second harmonic, what's it?
Yeah.
There is a way to check. I think somebody told me about a very clever way to check if it's a second harmonic. I just can't remember. So with 3 pulses or some very clever way. There are clever ways to check whether it's a second. We haven't done that.
It would be a nice addition to maybe a window of Fourier transform analysis.
We have done all the Fourier transform analysis, and the only reason I'm not showing it is because all these here at least you have no shoulders, but for the current you have all these shoulders, and we don't know what's going on.
So, yeah, thank you. So, catching on this, on the question of of the contact. I mean, the physics that you have in tunneling is quite different from the physics that you have in contact.
Correct.
In contact, you are measuring in the Robinson probably and ballistic case. So, what is your feeling of what you are measuring as function of time?
So that there is not actually easier than the STM.
I understand that the signal is bigger.
No, no, not that, not that. And then it's easier to interpret in some ways than the SDM because the current is truly oscillating. In emission,
Oscillating that way.
it's oscillating, yeah, but it's a 1D signal. That helps. It's a one-dimensional signal, so everything's happening in one dimension. That really helps. So there, I would say we're just picking up the current itself, direct current oscillations of the phase mode. Whereas in STM, that's the mystery. What are we picking up in the STM, and why are we seeing these ones in STM?
But in the point contact, do these curves depend on the bias?
Yes. And
So
so
are you below or because you can excite form?
no. So this is an insulator, and so I'll show you what it looks like as a function of bias. So this is the gap, right? And but remember what this is. This what I'm showing you here is the intensity divided by the current. It's delta I over I, because our signal strength depends on the current. So this is delta I over I. So that delta I over I has a peak inside the gap. So that's what it looks like.
Thank you.
Sure.
No, I have like many tiny questions about minor details, but more or less explain.
Okay.
Yeah, thanks for the talk. So I just have curiosity because I'm not very familiar with the technique. So how can you combine the atomic resolution of SPM with this? Because I guess what you get, at least in the SPM, is an average signal. So how do you get
In the actual STM?
Yeah, when you do the time of SPM, so the signal you get is what you get from I don't know, from the spot of the light you have. Or it's really local. That's my way.
Yeah, it's a
how
good
the
question.
expression differ
Yeah.
wherever it can be evaluated.
Yeah, so that the signal is localized, in the sense that because it's tunnel current and because the current is really coming from this exponentially decaying states, etc., that signal is localized. And after this, we've done a lot of work on other things. For example, right now we're looking at a topological crystalline insulator, which has some edge states, and we can really see, we can go to the edge and we can see a signal that's different from the bulk. So we have really good spatial resolution. And so the tunnel current signal is pretty well localized. However, the actual physics is happening over very large scales. So even though our tunnel current information that we're getting is a local information, the physics is happening over large length scales. So yeah, that is true, but that's true for many systems anyway. Yeah.
Welcome.
Hi, thank you for your talk. So I'm wondering a bit, when you do the reflectivity measurements, so you're basically, when you do pump probe, you discard the pump measurement by the polarization. But the thing is that when you couple different polarizations of light to a tip sample system, they do not enhance in the same way, either by plasmonic enhancement or by confinement. So then I'm not sure if rotating the polarization of the pump sheet is gonna affect your measurement.
So this is we've done both. So this is the probe polarization and rotation. We've also done the pump polarization, which has no features.
So you rotate the pump polarization and it doesn't affect your risk.
No,
Oh.
But the probe does.
Oh.
Yeah.
Okay.
So, any other questions?
Yeah.
Yeah.
You have to get it out of the tiny questions.
No, that's very much. When you want to do experiment, you spatially resolve experiments on different positions of the chart density way.
That is hard. We have done it, but that's hard. The reason it's hard is because the clear surface in this material is iodine. And iodine, after like 5 minutes of the tip being there, it sometimes pops out. and it's very loosely bound. So we have done spatially resolved measurements, but we can't compare it does look like the amplitude is changing as a function of position. But then suddenly there's a missing iodine atom and it completely destroys our night data. So we haven't pursued it really, because it keeps popping out the iodine. The tip is probably enhancing the electric field locally, and that's popping out the iodine. And the thing is, the longer you stay there, the larger the probability of that happening. So for this thing, we go to a certain point, sit there, take data, move, take data, and it takes a few minutes to get the spectrum. And so, yeah, that's
Okay. More questions? No? Okay, then thanks, Vidya, again for the talk.